The strongest metal on Earth wasn't discovered by accident. It was hidden, deep in the ground, locked away in chemical chains so tight that even nature struggles to break them. And when we finally figured out how to extract it, when we cracked the code in 1940, we didn't just find a metal. We found something that would change aerospace, medicine, weapons systems, and the human body itself. But here's what most people don't realize. Titanium doesn't naturally exist in a usable form. It's a prisoner of chemistry. And the process to free it? It's one of the most violent, expensive, ingenious procedures in industrial history. If you find this as mind-bending as I do, hit like and drop a comment. Let's see who else is fascinated by the hidden complexity of everyday materials. Titanium is the 9th most abundant element in Earth's crust. Let that sink in. It's everywhere, practically under your feet right now. Yet despite existing in such abundance, pure titanium is rarer than you'd think. Why? Because titanium is obsessed with oxygen. The moment it touches oxygen, and oxygen is everywhere, they bond. They lock together. They form titanium oxide, titanium dioxide, titanium compounds so stable that separating them requires industrial-scale violence. Nature doesn't want to give up titanium. It never did. So for thousands of years, humans didn't have it. We had iron, copper, bronze, but not titanium. We didn't even know titanium existed until 1791, when a British clergyman named William Gregor found it in an obscure sample of iron sand. It sat in museums, a scientific curiosity, nothing more, until we needed it. And then everything changed. After World War II, aircraft were pushing beyond the limits of aluminum. The faster they flew, the hotter the engines became. Aluminum melts. It crumbles. We needed something stronger, something that could withstand temperatures that would liquefy steel. Engineers looked at titanium and saw the solution. But there was one catastrophic problem. We had no idea how to extract it. A German chemist named Wilhelm Kroll had been working on the problem for years. In 1940, working in Luxembourg, he finally cracked it. The Kroll Process. A method so complex, so demanding, that it would take decades to make it practical. And even today, extracting titanium from ore is one of the most energy-intensive, expensive procedures in metallurgy. So how exactly does it work? How do you tear titanium away from the chemical bonds that refuse to let it go? It starts with something you wouldn't expect. The ore itself isn't the problem. Australia, South Africa, Canada, these countries pull titanium ore from open-pit mines using heavy machinery. The ore is crushed, washed, separated from the surrounding rock. This part is brutal but straightforward. Brute industrial force. The real problem begins in the laboratory. The ore contains titanium minerals, ilmenite and rutile. These aren't pure titanium. They're titanium locked in chemical prisons. And to liberate the titanium, you have to break those prisons. Systematically, deliberately, with methods that seem almost alchemical. Here's what Kroll discovered. If you take crushed ore and mix it with chlorine gas and carbon coke, then heat it to nearly 1000 degrees Celsius, something remarkable happens. The chlorine doesn't just touch the titanium, it attacks it. It rips oxygen away. The titanium and chlorine bond instead, forming titanium tetrachloride. Titanium tetrachloride is volatile, toxic. If it touches water, it explodes into a cloud of corrosive acid. It's one of the most dangerous liquids in the industrial world. But it's also pure, because the iron, the other metals, the impurities, they don't react the same way. They stay behind as solid waste while the titanium tetrachloride vaporizes. You now have liquid titanium. But it's not metal. It's a chemical compound that looks nothing like the silvery, impossible material you're trying to create. The next step is where the process becomes genuinely extreme. The titanium tetrachloride is distilled to remove any remaining contamination. Then it's exposed to something that most people have been taught to fear: molten magnesium or sodium. In a vacuum chamber, in an environment stripped of oxygen. When molten magnesium meets titanium tetrachloride, the reaction is violent. The magnesium steals the chlorine. The titanium falls out as a byproduct, a spongy, porous form of the metal called titanium sponge. It looks like a burnt, irregular rock. Not impressive. Certainly not like the strong, shiny titanium that ends up in aircraft engines and prosthetic limbs. This is where most people think the process is complete. It isn't. The titanium sponge is still contaminated, still porous, still weak, so it's melted. Using vacuum arc remelting or electron beam melting, the sponge is heated to 1,700 degrees Celsius. Any remaining impurities burn away or evaporate. The liquid titanium flows into a mold. It cools. It solidifies into an ingot, a massive block of pure, homogeneous titanium metal. For the first time, after all this violence, all this chemical warfare, you have something recognizable. But you still don't have a product. The ingot is reheated and forced through industrial presses, rolled, extruded, shaped into sheets, rods, tubes, whatever the intended application demands. The titanium is heated again and again, pushed through industrial machinery that exerts thousands of tons of pressure. It resists. Titanium is notoriously difficult to shape. It's so hard, so resistant to deformation, that normal tools fail. Special high-temperature alloys are required. Cutting speeds must be precise, or the tools shatter. Then comes alloying. Small amounts of aluminum, vanadium, molybdenum. Elements are added to the molten titanium to create specific properties. Aerospace titanium is different from medical titanium, different from titanium used in military applications. Each alloy is engineered for a purpose. After shaping, the titanium undergoes machining so precise that tolerances are measured in fractions of a millimeter. Special tools, coolants, techniques that have been refined over decades. For medical implants, the finished titanium is polished to a mirror-like shine and treated to enhance biocompatibility. The surface becomes something your body recognizes as safe. Your immune system accepts it. It integrates. For aerospace applications, the titanium receives heat treatments that reorganize its crystal structure, making it stronger, more durable, more capable of surviving the impossible stresses of flight. And now, only now, do you have the final product. But here's the twist. Despite all this effort, despite the energy costs, the chemical complexity, the precision engineering, titanium's production isn't efficient by modern standards. The Kroll process wastes material. It generates byproducts that must be carefully managed. It consumes enormous amounts of energy. Yet we keep doing it. We keep doing it because there is no alternative material that does what titanium does. It's strong, yet lightweight. It resists corrosion. It survives extreme temperatures. It's inert. Your body won't reject it. Your aircraft won't fail at it. There's a new process emerging, the FFC Cambridge method, which uses electrolysis instead of chemical reduction. It's more efficient, more sustainable, but it's not ready for mass production. Not yet. So we're still using a 70-year-old process, perfected and refined but fundamentally unchanged, to create the most advanced materials in the world. Titanium's journey from ore to finished product isn't just a manufacturing story, It's a metaphor. It's a reminder that complexity is often invisible, that extraordinary materials require extraordinary effort, that the sleek, finished products we take for granted, aircraft, smartphones, prosthetics, spacecraft, represent not just engineering but chemical warfare waged against nature's reluctance to let us reshape the world. The next time you see something made of titanium, you're looking at dozens of people, thousands of hours of research, industrial processes that push the boundaries of what's chemically possible, all condensed into a single object. You're looking at human persistence, human ingenuity, human refusal to accept that something is impossible just because it's difficult. And honestly, that's worth knowing.